Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler and today we're going to be doing Unit 3, Lesson number 4 on limit tricks. So, we've been doing a lot of different limits lately, graphically, using tables on our calculator, and even doing a lot of limits by substitution. Remember, the key with substitution is the idea that if an expression or a function is continuous at a particular target value of x, we can figure out what its limit is simply by plugging in the value of x and calculating. Today, we're going to see two of the more common limit tricks that we can employ when we can't do a limit by substitution. All right? So let's dive right into it. Exercise number 1, very simple. Determine the value of the limit as x goes to 1 of x squared minus 1 divided by x plus 1. Please go ahead and do that. All right, well, this is a very simple limit, right? And it's a simple limit because around the target value of x equals 1, this expression is defined, right? So we can just do it by substitution. The limit as x goes to 1 of 1 squared minus 1 divided by 1 plus 1 would be 1 minus 1 divided by 2, and that would be 0 divided by 2, which equals 0. All right, so simple enough, right? Easy, easy. And it's easy because, again, that expression is defined and continuous for all x values around x equals 1 and at x equals 1. All right, I'm going to clear this text out, and then we're going to go on and do something that's worth our time. So let's move on to the next problem. Now let's consider the limit as x goes to 1 of x squared minus 1 divided by x minus 1. Letter A. Why can't this limit be performed using substitution? Think about that for a moment. All right. Well, if you said something like, upon substitution, we're forced to divide by 0, that would be a good answer. In fact, right, if I did this limit exactly like I did the other one, I'd get 1 minus 1 divided by 1 minus 1, and that would be 0 divided by 0, and that is undefined. Well, 0 isn't undefined, but dividing by 0 is undefined. Okay? Now, letter B says, use factoring techniques to determine the value of this limit. Check using tables on your calculator. All right? So let's take a look. All right, this is very important, so let's take it nice and slow. The limit as x goes to 1, I can factor that numerator into x minus 1 times x plus 1, all divided by x minus 1. Now, almost all of our algebraic training at this point says that we should cancel these. All right. Now, this ends up being the limit as x goes to 1 of x plus 1. All right, we're going to make a comment on this in just a moment. But now think about this. This can easily be done by substitution. X plus 1 is nicely continuous when x is equal to 1, so I substitute it in and I get 2. All right. Let's verify this using a table on our calculator. All right, so let's open up the TI-84 Plus. All right, let's go into our y equals button. Remember how we did this from a few lessons ago? In y1, let's put in x squared minus 1 divided by x minus 1. Okay, make sure that you've got that in there correctly. Now remember, what we're going to do is we're going to go into our table setup next, so let's do that. Let's go into table setup. It's right up here. Let's start our table at x equals 1, and let's go by, I don't know, let's say 0.01, so by hundredths. You could go by thousandths as well. You just want to get really close to x equals 1. All right, once we have our table start and our delta table all set up, let's go into the table and look. All right, let me pan up a little bit here so that we get our x equals 1 right there in the viewing frame. Notice, right, it's an error. It's undefined at x equals 1. But take a look, right? As we're approaching 1 from the left, right, we're getting numbers like 1.98, 1.99. As we approach it from the right, we're getting numbers like 2.02, 2.01. So I think that we can conclude based on that our limit of 2 is correct. All right, and that's all we needed the calculator for, so I think we're going to put it back away now. All right, bye-bye. Now, let's talk about letter C. It says, why is it okay to substitute x equals 1 into the reduced rational form, even though the reduced rational form is not valid when x is 1? So let's talk about something here a little bit. All right, forget about that question overall. I want to talk a little bit about equivalence. All right, so in previous courses, you have probably very often written stuff down like this. Now, there's a little bit of a problem here. Equality is what's called transitive. So if A is equal to B and B is equal to C, then A is equal to C. All right, real easy. It's called the transitive property of equality. Oops, that didn't work. I'm just going to erase that. So in other words, what we're saying here is we're saying that x squared minus 1 divided by x minus 1 is equal to x plus 1. And that is, in the strictest sense, not true. They are equal for every value of x, but not x equals 1. Because clearly this expression is defined at x equals 1, whereas this expression is undefined at x equals 1. And that's important. You know, you may have had some math teachers in the past that always said, okay, when you cancel out repeated factors in the numerator and denominator, always put down, oh, x can't be equal to the following, or x can't be equal to the following. Teachers that made you do that were doing you a service, not a disservice. In fact, the teachers that didn't say to do it, they were doing you a disservice. I mean, yeah, sure, it's quicker not to have to list all the values of x for which a reduction is not valid, but it's really important. That's what this question is getting at. This question is saying, well, why can I do this? I mean, this reduction is only valid when x doesn't equal 1. So why am I now allowed to throw x equals 1 in there? Think about this for a little bit. All right. Well, the reason why, it's valid because we never reach x equals 1 in the limit. Again, I want you to really think about this because it's a very deep idea. A limit is never asking, what does the expression or the function reach when x reaches a value? It is asking, where is a function or expression headed towards as x heads towards a value? So since we could literally put in 1.0000001 or 0.999999, since we can literally put that into this rational expression, then we can also substitute it into the x plus 1, because the x plus 1 is valid everywhere but x equals 1. And surely when x is 0.99999999, x plus 1 is very close to 2. And when x is 1.0000001, x plus 1 is very close to 2. So even though that expression, the original expression, doesn't exist when x is 1, it is certainly headed towards 2 as x gets infinitesimally close to 1. I know it took a long time to go through that, but it's really important. Finally, letter D. What type of graphical feature would this thing have on it when x is 1? Well, think about it. This function and this function are identical, except this function just doesn't exist when x is 1, right? So what we have is we've got a nice line, right? Nice line, but right at x equals 1, it simply doesn't exist. So it's got a hole, right? It's got a hole. A hole at x equals 1. The fancy term for that is it's got a removable discontinuity, but we'll talk more about those later. All right, pause the video and write down anything you need to before I scrub out the text. All right, let's do it. So, what's our first technique? What's our first limit trick? Factor cancel. Now, just a little bit of red flag kind of thing. Factor cancel will tend to work very well if after you substitute into your limit, you get 0 divided by 0. 0 divided by 0. Limits that upon substitution give you 0 divided by 0 are the most interesting limits of all. The most interesting of all. And we'll understand why that is as we develop calculus more and more. But those are the most interesting limits of all. So if you substitute and you get a 0 divided by 0 scenario, you should be looking to factor. So why don't you try letter A? All right, let's go through it. And let's not just only go through it, let's make sure we understand the notation. A lot of people kind of get confused about how long they should keep the limit and how long they shouldn't. Now, I'm going to just say without doing any work that this does end up being 0 over 0 upon substitution. Now, what's one thing that's kind of cool is because we're getting 0 as x goes to 3, x minus 3 must be a factor of the numerator. Now, that's something that you should have learned in previous courses, but that means it should be very easy to factor, right? You know, if we know one of the two factors, the other factor, the 2x plus 1, should be very, very easy. In fact, this then cancels, and we'll get the limit as x goes to 3 of 2x plus 1. And now I can substitute, right? And I'll get 2 times 3 plus 1. Notice something. I dropped the limit, right? Notice here I've dropped the limit. No more limit. And the reason is, at that point, I've really found the limit. I mean, I don't have the final answer. I don't have x equals 7. Or I'm sorry, I don't have the limit equals 7. It's not x. X is going to 3. But there's no more limit because I have actively substituted to try to find it. Likewise, notice that the limit is still sitting here because I haven't yet evaluated the limit. I'm saying, hey, the limit of this is equal to that, and the limit of that is equal to that limit, and that limit is equal to here, and I don't have the word limit there anymore because I've actually found the limit. All right. Well, if you haven't tried letter B yet, pause the video now and try to work through that one as well. All right. Well, yet again, because we get 0 divided by 0, x plus 5, right? X plus 5 must be a factor of both the numerator and the denominator. That's actually kind of important. The denominator is pretty easy to factor, right? It becomes 3 times x plus 5. The numerator is more of a challenge. Maybe I'll do that kind of down here. That's actually some factoring by grouping, right? I can factor an x squared out of the first two terms, leaving me with an x plus 5. And I can factor out a negative 2 from the other two terms, leaving me with a negative 2 times x plus 5. So in total, I'll have x squared minus 2 times x plus 5 as the factoring of the numerator. Those two cancel. I've now got the limit as x goes to negative 5 of x squared minus 2 divided by 3. And now watch as I drop the limit because I'm now going to evaluate by substitution. And I'll get 25 minus 2 divided by 3 gives me 23 thirds. Not the nicest limit on earth, but we'll live with it. All right. Now again, notice that these limits exist because it's sort of like we have this factor in both the numerator and the denominator that's both going to 0. And it's going to 0 sort of at the same location in x. Because of this, we can cancel it out, and what we're effectively getting is a hole in the graph. We're getting just this little pinprick that we remove at that one particular value of x, and that allows us then to evaluate the limit once we cancel it out. Pause the video now and write down what you need to. Okay, here we go. Let's keep going. All right. Now we're going to look at a completely different type of limit. One that, hey, for lack of a better term, has square roots in the numerator. Not cubed roots, not fourth roots, square roots. All right? And this is a technique affectionately called rationalizing the numerator. So a little discussion before we move on. Okay, discussion down here. Last year you had to deal with some really obnoxious problems, like something like this. 5 divided by 2 minus the square root of 3. And they would say, rationalize this. Rationalize this. Or rationalize the denominator. And the way that you would do that is you would multiply both numerator and denominator by the conjugate of that binomial. And the reason you do this is that anytime you multiply a plus b times a minus b, you get a squared minus b squared. We're not going to go into why that is. But when you have radicals involved, what this becomes is 2 minus root 3 times 2 plus root 3 ends up being 2 squared minus root 3 squared, which is 4 minus 3. In this case, that's 1. Here's the key thing, though, is that that radical being squared, then those two operations cancel each other. Okay? Strangely enough, we're not going to use that at all. What we're going to use is we're going to rationalize the numerator. Now, I would like to just point out, again, that if you substituted x equals 0 in here, you would get a 0 divided by 0 scenario. Take a look. You'd have the square root of 4 minus 2, which would be 2 minus 2. That would be 0. And then, of course, the denominator is also 0. Now, what I'm going to do is I'm actually going to multiply by the conjugate of the numerator. All right. Now, we're going to be very, very careful about our parentheses use here. But really, we have an a minus b times an a plus b scenario. And let me just do something really quick. Let me really make sure you get it. Minus b. So a is this entire thing, and b is the 2. So what I'll get is I'll get root 4 plus x squared, which is just 4 plus x, minus 2 squared, which is 4. The denominator, again, let's be very good about our parentheses use, very good about it, right, is going to look something like that. Now, if I let the limit as x goes to 0, these two cancel, and I'll get x divided by, oh, this is going to be a little tight, square root of 4 plus x plus 2. And notice the whole thing, the thing that was preventing me from substituting in the first place was that thing going to 0. And notice it cancels, right? So now I have the limit as x goes to 0 of 1 divided by the square root of 4 plus x plus 2. I can now substitute, in which case I'll drop the limit as soon as I substitute. Now I'll get the square root of 4 plus 2. And that's 1 divided by 2 plus 2. Whew, and that's a limit of 1/4. If you actually put that into your calculator, and you've done this limit before, I think you had it on homework, if you put that limit in your calculator, you'll also find 1/4. All right? Rationalizing the numerator. Write down what you need to, and then we'll go on and do another one of these. All right, let's move on. Oh, come on, page. There we go. Evaluate the limit as y goes to 10 of root y plus 6 minus 4 over 2y minus 20. Now again, if you substituted, what you would end up getting is root 16 minus 4 divided by 20 minus 20, which would be 4 minus 4 divided by 20 minus 20, and that would be 0 divided by 0, right? Most interesting limits. Now, one thing that's important to understand, or at least helpful to understand, I don't know if it's important, but it's definitely helpful, is that the reason that this limit is problematic, the reason we have to do it by substitution, really isn't about the 2y minus 20. It's about the fact that that's 2 times the quantity y minus 10. It's that factor of y minus 10 sitting there. In a certain sense, one could almost say that there's a y minus 10 also in the numerator. But I don't want to get too deep into that. A lot of students struggle seeing that, so there's no real need for it. So what I'd like you to do is pause the video and see if you can do this problem by rationalizing the numerator. And if not, obviously we're going to be doing it in a moment anyway. All right, let's go through it. Again, watch how much I keep the limit, and I will be very clear about when to drop it. Limit is y goes to 10 of root y plus 6 minus 4 divided by 2y minus 20 times root y plus 6 plus 4 times root y plus 6 plus 4. All right, this is equal to the limit as y goes to 10. Now again, I know that it's not about 2y minus 20, it's about y minus 10. So I'm going to immediately factor that 2 out. Now I've got this a minus b times a plus b. So a squared will be y plus 6, b squared will be 16. Keep going. Limit y goes to 10. Y minus 10 now in the numerator. 2 times y minus 10 times root y plus 6 plus 4. And they're gone. The offending factor, that's what I call it. The offending factor has canceled. Right? And because of that, I can now look at the limit as y goes to 10 of 1 divided by 2 times root y plus 6 plus 4. And now notice as I substitute, I will drop the word limit. Whew. Good parentheses use is helpful. My final answer is 1/16. Make sure that's right. Oh yeah, still is. Excellent. Oh, that made my hand hurt. Okay, well, pause the video now and copy down anything you need to about this rationalizing problem. All right, clearing out the text, and then we'll do one more problem. Okay, this is a very AP-like problem. The previous problems certainly could find their way onto the AP exam, but this is very AP-like because it pushes to see whether you really understand the process that's going on here. It says, given that the limit as x goes to 3 of the square root of x plus k minus 3 over x minus 3 exists for some real value of the constant k, so k is just some number we don't know, do the following. Find the value of k, and then find the value of the limit. Oh boy. Okay, well there's a couple different cool ways to do this, so I'd like you to pause the video now and play around with it. And if you have no idea where to start with this. Start by trying to evaluate the limit. I know you don't know what k is, but start by trying to evaluate the limit and see if something occurs to you along the way. All right, let's go through it. There's actually a lot of great different ways to do this problem. But again, I'm gonna kind of go down that path that I was describing. You know, hey, if I have nothing else that I can do, maybe I'll just do what I've been doing in the last couple problems. So in other words, I think I'll rationalize it. X plus k plus 3 and root x plus k plus 3. I don't know. Let's see what happens. I'll get x plus k minus 9 divided by x minus 3 times root x plus k plus 3. All right, now here's the thing, right? In order for me to evaluate this limit, the offending factor, let me draw it in red, the offending factor, this has to cancel. If that doesn't cancel, has to cancel. If that doesn't cancel, then I won't be able to do this problem. And the only way it'll cancel is if x plus k minus 9 is equal to x minus 3. Right? It has to cancel with this. Right? That whole numerator has to cancel that x minus 3. Well, the x's are the same, so then k minus 9 must be negative 3, and k must be equal to 6. So the only way this limit exists is if k is equal to 6. All right, now find the value of this limit. Well, now we just rationalize again. X goes to 3, square root of x plus 6 minus 3 over x minus 3, right? So we rationalize, multiply by x plus 6 minus 3 and root x plus 6 minus 3. And we'll get the limit as x goes to 3 of x plus 6 minus 9 divided by x minus 3 times root x plus 6 plus 3. Notice the parentheses there and there, right? This is going to be x minus 3, so cancel. So I have the limit as x goes to 3 of 1 divided by root x plus 6 plus 3. Now I substitute, so I drop the word limit, and I'll have 1 over 3 plus 3, or 1/6. And that's it. That is it. So that's kind of cool. Very AP-like, because you really have to realize that what makes that limit exist mechanically is having that factor that's going to 0 in the denominator cancel out, and it's got to cancel with the numerator. All right. Well, pause the video now and write down anything you need to. All right, time to clear stuff out. Wrap up the lesson. Oh yeah, let's do it. So we're going to see some other algebraic tricks in the next couple days, but they're not as broad as the ones that we saw today. All right. Now, first and foremost, when you're doing a limit algebraically, you should try substitution. If the function is defined there with some exceptions like piecewise functions and square root functions, then you can evaluate the limit just by substitution. On the other hand, if you get these special limits that upon substitution turn out to be 0 divided by 0, then you should look for one of the two techniques we had today, factor cancel, in the case of a polynomial divided by a polynomial, or rationalizing the numerator in the case where we have a square root expression or an expression involving a square root in the numerator. All right. Well, I'd like to thank you for joining me for another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.